To interconnect electrical panels, first, install a main disconnect switch. Locate a central location downstream of all utility meters. Install a disconnect switch rated for at least 300 amps, which is the amperage of the service upgrade plan for the first floor. Secondly, wire the main disconnect switch. Run service entrance cable from the utility meter to the main disconnect switch. Connect the incoming power cable to the line side of the disconnect switch. Connect the load side of the disconnect switch to the main lug in the 300 amp service panel on the first floor. Thirdly, install a split breaker in the main service panel. This breaker will have two 100 amp poles that will provide power to panels number 2 and number 3. Fourthly, wire the split breaker. Connect the upper, or line, terminal of the split breaker to the main lug in the service panel. Connect the lower, or load, terminals of each pole of the split breaker to two separate 100 amp feeder breakers. Fifthly, wire the feeder breakers. Run 100 amp service entrance cable from each feeder breaker in the main service panel to the panels on floors number 2 and number 3. Connect the service entrance cable to the main lug in each panel. Sixthly, install breakers in panels number 2 and number 3 to protect the branch circuits. It is important to ensure all wiring and components meet current electrical codes. Consider consulting with a licensed electrician for proper installation and safety. Switching from multi-family to single-family is straightforward. To switch from multi-family to single-family, you can simply disconnect the feeder breakers connecting panels number 2 and number 3 in the 300 amp service panel on floor number 1. This will isolate the electrical systems for each floor. For further information, consult the National Electrical Code, Article 230, and split breaker guides. When planning this project, several factors need consideration for a safe and compliant installation. These include the correct sizing of conductors, proper overcurrent protection, and adherence to local electrical codes. A National Electrical Code, or NEC, provides detailed guidelines for these aspects. Firstly, conductor sizing is critical. The conductors must be sized appropriately for the load they will carry. The ampacity of the conductors, that is, their current carrying capacity, must be sufficient to handle the expected load plus any applicable directing factors. For example, conductors installed in conduit with other conductors may need to be derated to account for the increased heat. Secondly, overcurrent protection is essential for safety. Circuit breakers or fuses are used to protect the conductors from overloads and short circuits. The overcurrent protection device must be sized to protect the conductors, but it should not be larger than the ampacity of the conductors. For example, a 12 American wire gauge copper conductor, which typically has an ampacity of 20 amps, should be protected by a 20 amp circuit breaker. Thirdly, grounding and bonding are critical for safety. Grounding provides a path for fault current to flow back to the source, which allows the overcurrent protection device to trip and clear the fault. Bonding ensures that all metallic parts of the electrical system are at the same potential, which reduces the risk of electric shock. The NEC specifies detailed requirements for grounding and bonding. Fourthly, working space around electrical equipment is necessary for safety and accessibility. A NEC requires that sufficient working space be provided around electrical equipment to allow for safe operation and maintenance. The working space must be clear and unobstructed. Fifthly, arc fault circuit interrupters, or size, and ground fault circuit interrupters, or GFCIs, are important safety devices. A size protect against arc faults, which can cause fires. GFCIs protect against ground faults, which can cause electric shock. The NEC requires a size and GFCIs in certain locations, such as bedrooms and bathrooms. Sixthly, conduit and cable routing must be done carefully. Conduit and cable must be properly supported and protected from physical damage. The NEC specifies requirements for conduit and cable routing. Seventhly, labeling is important for identifying circuits and equipment. All circuits and equipment must be clearly labeled to indicate their purpose. The NEC specifies requirements for labeling. Eighthly, documentation is essential for future reference. Keep accurate records of all electrical work, including wiring diagrams and equipment specifications. This documentation will be helpful for future maintenance and troubleshooting. Ninthly, local electrical codes may have additional requirements beyond the NEC. It is important to check with the local electrical inspector to ensure that all work complies with local codes. Tenthly, professional installation is recommended. Electrical work can be dangerous, so it is recommended to hire a licensed electrician to perform the work. A licensed electrician will have the knowledge and experience to ensure that the work is done safely and correctly. The project involves upgrading the electrical service to 300 amps on the first floor while maintaining 100 amp service on the second and third floors. This requires careful planning and execution to ensure a safe and reliable electrical system. To reiterate the key steps, the first step involves installing a main disconnect switch. The main disconnect switch should be located downstream of all utility meters and rated for at least 300 amps. The second step is wiring the main disconnect switch. Run service entrance cable from the utility meter to the line side of the disconnect switch. Connect the load side of the disconnect switch to the main lug in the 300 amp service panel on the first floor. The third step is installing a split breaker in the main service panel. A 300 amp split breaker with two 100 amp poles can be used to provide power to the 100 amp panels on the second and third floors. The fourth step is wiring the split breaker. Connect the line terminal of the split breaker to the main lug in the service panel. Connect the load terminals of each pole of the split breaker to separate 100 amp feeder breakers. The fifth step is wiring the feeder breakers. Run 100 amp service entrance cable from each feeder breaker to the 100 amp panels on the second and third floors. Connect the service entrance cable to the main lug in each panel. The sixth step is installing breakers in panels number 2 and number 3 to protect the branch circuits. Proper grounding and bonding are essential for safety. Grounding provides a path for fault current to flow back to the source, which allows the overcurrent protection device to trip and clear the fault. Bonding ensures that all metallic parts of the electrical system are at the same potential, which reduces the risk of electric shock. The NEC specifies detailed requirements for grounding and bonding. Ensure that all wiring and components meet current electrical codes and consult with a licensed electrician for proper installation and safety. Consider the following steps when implementing this electrical panel interconnection. Firstly, calculate the total load. Before starting any electrical work, it's essential to accurately calculate the total electrical load for each floor. This involves adding up the amperage requirements of all appliances, lighting, and other electrical devices that will be used simultaneously. This calculation will help you determine the appropriate size of the service panel, breakers, and wiring needed for each floor. Secondly, select the appropriate service panel. Choose a service panel that is appropriately sized for the calculated load. The service panel should have enough breaker slots to accommodate all the circuits needed for each floor, with some spare slots for future expansion. The service panel should also be rated for the appropriate voltage and amperage. Thirdly, install the main disconnect switch. The main disconnect switch should be installed in a readily accessible location, such as near the service panel or the utility meter. The disconnect switch should be rated for the full amperage of the service and should be capable of disconnecting all power to the building. Fourthly, install the grounding system. A proper grounding system is essential for safety. The grounding system should consist of a grounding electrode, such as a ground rod or a metal water pipe, and a grounding conductor that connects the grounding electrode to the service panel. The grounding system should be installed in accordance with the NEC. Fifthly, run the service entrance cable. The service entrance cable should be run from the utility meter to the service panel. The service entrance cable should be sized appropriately for the amperage of the service and should be protected from physical damage. The service entrance cable should be installed in accordance with the NEC. Sixthly, install the circuit breakers. The circuit breakers should be installed in the service panel and wired to the appropriate circuits. The circuit breakers should be sized appropriately for the amperage of the circuits and should be installed in accordance with the NEC. Seventhly, label the circuits. Each circuit breaker should be labeled to indicate the circuit it controls. This will make it easier to identify and troubleshoot circuits in the future. Eighthly, test the system. After all the wiring is complete, the system should be tested to ensure that it is working properly. This should include testing the voltage, amperage, and grounding system. Ninthly, obtain an inspection. After the electrical work is complete, it should be inspected by a qualified electrical inspector. The inspector will ensure that the work is done in accordance with the NEC and local codes. Tenthly, document the work. Keep accurate records of all electrical work, including wiring diagrams, equipment specifications, and inspection reports. This documentation will be helpful for future maintenance and troubleshooting. When selecting the appropriate size of conductors, consider the ampacity, voltage drop, and dating factors. Firstly, ampacity refers to the maximum current a conductor can carry without exceeding its temperature rating. The NEC provides tables that list the ampacity of various conductors based on their size, insulation type, and installation method. Select a conductor with an ampacity that is equal to or greater than the calculated load. Secondly, voltage drop refers to the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause appliances and equipment to operate inefficiently or even fail. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Use voltage drop calculators or consult the NEC to determine the appropriate conductor size to minimize voltage drop. Thirdly, dating factors or adjustments to the ampacity of a conductor that are necessary when the conductor is installed in certain conditions, such as in conduit with other conductors or in high-temperature environments. The NEC provides tables that list dating factors for various installation conditions. Apply the appropriate dating factors to the ampacity of the conductor to ensure that it is not overloaded. When implementing overcurrent protection, consider circuit breakers versus fuses, sizing the overcurrent protection, and selective coordination. Firstly, circuit breakers and fuses are both overcurrent protection devices that are designed to interrupt the flow of current in a circuit when an overload or short circuit occurs. Circuit breakers are resettable devices that can be tripped and reset multiple times, while fuses are one-time devices that must be replaced after they blow. The choice between circuit breakers and fuses depends on the application and personal preference. Secondly, the overcurrent protection device should be sized to protect the conductors and equipment in the circuit. The NEC provides guidelines for sizing overcurrent protection devices based on the ampacity of the conductors and the type of equipment being protected. Ensure that the overcurrent protection device is sized appropriately to prevent overloads and short circuits. Thirdly, selective coordination refers to the practice of coordinating the overcurrent protection devices in a system so that only the device closest to the fault trips, minimizing the disruption to the rest of the system. Selective coordination is important in critical applications where downtime must be minimized. The NEC provides guidelines for selective coordination. Grounding and bonding procedures are important to adhere to. Consider grounding electrodes, grounding conductors, and bonding. Firstly, grounding electrodes are conductive objects that are used to establish a connection to the earth. Common grounding electrodes include ground rods, metal water pipes, and concrete encased electrodes. The NEC specifies requirements for the type and size of grounding electrodes. Secondly, grounding conductors are used to connect the grounding electrode to the service panel and other electrical equipment. The NEC specifies requirements for the size and installation of grounding conductors. Thirdly, bonding is the process of connecting all metallic parts of an electrical system together to create a low impedance path for fault current. Bonding helps to prevent electric shock and fire hazards. The NEC specifies requirements for bonding various metallic parts of an electrical system, such as metal conduits, enclosures, and equipment. When you are considering working space and access, think about clearances around equipment, dedicated equipment space, and illumination. Firstly, clearances around electrical equipment are necessary to provide adequate working space for electricians to safely install, maintain, and repair the equipment. The NEC specifies minimum clearances around electrical equipment based on the voltage and amperage of the equipment. Secondly, Dedicated equipment space is the space that is reserved for electrical equipment and should not be used for storage or other purposes. The NEC specifies requirements for dedicated equipment space. Thirdly, adequate illumination is necessary to provide safe working conditions for electricians. The NEC specifies minimum illumination levels for electrical equipment rooms and other work areas. When considering arc fault circuit interrupters and ground fault circuit interrupters, think about the locations where they are required, testing the devices, and the differences between them. Firstly, FSIs and GFCIs are required in certain locations to protect against electrical hazards. The NEC specifies the locations where FSIs and GFCIs are required, such as bedrooms, bathrooms, and kitchens. Secondly, FSIs and GFCIs should be tested regularly to ensure that they are working properly. Test buttons are provided on the devices for this purpose. Thirdly, FSIs protect against arc faults, which are dangerous electrical arcs that can cause fires. GFCIs protect against ground faults, which are electrical faults that can cause electric shock. FSIs and GFCIs are designed to trip and interrupt the flow of current when an arc fault or ground fault is detected. Remember to consider conduit and cable routing considerations as well. Consider physical protection, support, and full capacity. Firstly, conduit and cable should be protected from physical damage to prevent electrical hazards. The NEC specifies requirements for protecting conduit and cable from physical damage. Secondly, conduit and cable should be properly supported to prevent them from sagging or becoming damaged. The NEC specifies requirements for supporting conduit and cable. Thirdly, the full capacity of conduit should not be exceeded to prevent overheating and damage to the conductors. The NEC specifies the maximum number of conductors that can be installed in a conduit of a given size. Remember to consider labeling and documentation as well. Consider circuit identification, warning labels, and record keeping. Firstly, circuits should be clearly identified with labels to indicate their purpose. This will make it easier to identify and troubleshoot circuits in the future. Secondly, warning labels should be placed on electrical equipment to warn of potential hazards. The NEC specifies requirements for warning labels. Thirdly, accurate records should be kept of all electrical work, including wiring diagrams, equipment specifications, and inspection reports. This documentation will be helpful for future maintenance and troubleshooting. All of this information is to provide a comprehensive understanding of the steps and considerations involved in interconnecting electrical panels. Always consult with a qualified electrician and adhere to local electrical codes to ensure a safe and compliant installation.